I would like to present a anti-poaching system for elephants, and the novelty is that it's animal-borne, so this is a wearable device. Unfortunately, our motivation is really sad, and this is ivory poaching, which is the illegal killing of elephants just for their tusks. In the last 60 years, many elephants were killed, and nowadays only around 500,000 left in Africa. And many of those animals live in huge reservations, but rangers cannot protect them in real time. One of the methods they try to use to protect the animals is using GPS tracking collars. This technology offers access to the location or the position of the animals, but not in real time. In this picture, you can see a GPS tracking unit on the top of the neck of a beautiful African elephant. This GPS tracking collar itself has three components. On the top, you can see the GPS tracking unit, and the collar itself is a machine belt, and at the bottom there is a counterweight to help to keep the tracking unit on the top. The deployment of such collars is very complicated and dangerous. The animal must be tranquilized before the deployment, and it requires a relatively big team. Once deployed, a sensor must work at least for 2 years. I want to note that this picture actually shows the deployment of our first prototype in Kenya. So the basic idea behind this wearable device is that we want to integrate a gunshot detector into these existing tracking collar units. So the new system can detect gunshots and send immediate alerts, and also GPS coordinates are included, so rangers can rush to the given position and catch the poachers. If that particular animal, because of course after we have detected bullets has been already fired, so probably the animal died, but the goal is to catch the poachers and somehow stop poaching. The abstract overview of our system shows that there is an existing part of the system, which includes the GPS localization and the communication part, and we're actually developing a new subsystem, the gunshot detection part, and we would like to we try to simplify the connection interface between the two to minimize the impact on the existing system, hardware and software designs. To better understand the challenges in that field, first we have to understand the basics of gunshot acoustics. There are two acoustic events associated with the firing of a typical supersonic rifle. One of them is the muzzle blast, which is caused by the hot, rapidly expanding gases leaving the barrel, and the other one is called the shockwave, or sonic boom, which is caused by the projectile traveling through the air about the speed of sound. This shockwave has a unique signal shape which resembles to a capital letter N. You can see it on the bottom of the slide. This particular shape has two impulse-like sections with sub-microsecond rising time. So these are pretty unique in the nature. Both acoustic events can be recorded by traditional microphones. Here you can see an example recording, the shockwave, the reflections, and after some delay you can measure or you can record the muzzle blast. We had to face several challenges. One of them was the sound quality drop. As I said earlier, the system has an existing part, so the enclosure was already designed, so we had to fit our subsystem into this enclosure, and it had a pretty strong metal frame and the nylon top, and the whole box is filled with resin before deployment. So sound must travel through the metal wall, and uh, there is a relevant quality drop. So a small hole is needed for the sound, but then we lose waterproofness. We solve this problem by applying acoustic vents. These are waterproof vents with acceptable sound transmission properties. Nowadays, they are commonly used in smartphones to provide waterproofness. Okay, the other major challenge was the power consumption problem. Gunshot detection requires the constant listening, recording, and processing of environmental noises and sounds, and this is power hungry. Current wearable counter-sniper systems can last for about 10 hours, and our requirement is 2 years. So you can feel the huge difference between the two time intervals. A possible solution is to put the system in a sleep mode and only wake up when there is an acoustic event and then start recording. But it has a major problem then, that is the following, that when we wake up, then we already lost a significant part of the shockwave pattern. And so there's an information loss, and we want to somehow preserve the full length of the shockwave, because it is the best indicator that a shockwave, that a gunshot event happened. Another possible solution is active listening that requires a constantly running analog to digital converter, and we are continuously keeping or storing a short history of the signal in the memory. So when there is a wake-up event, we already have some samples from the past, so we could record the full shockwave pattern. But this is a power-hungry solution because it needs actively running clock sources. So our solution solves both problems. It uses two microphones, and on this slide you can see the structure of our method or design. We mount a contact microphone on the surface of the metal enclosure, and this is also called a piezo pickup. And we have another microphone, a traditional electric microphone, which is placed at the end of a 3 centimeter long tube, and that 3 centimeter long tube separates the two microphones. In that state of the system, the CPU is in deep sleep mode and the microphone is turned off. When a shockwave hits the metal wall, voltage is being generated by the contact microphone, and we are using a normal analog comparator to trigger a wake-up event, and that trigger wakes up the CPU, actually the CPU now in run mode, and turns the microphone on. The shockwave continues its journey in the tube, and when it reaches the electric microphone, the system is already up and running and collecting digital samples. So the basic idea is to delay the incoming shockwave just by enough to provide enough time for the system to wake up. And here you can see an example recording with the proposed structure. The red signal shows the piezo pickup signal, and the black spike represents the time point of the wake-up trigger event, and the blue signal corresponds to the electret microphone signal, and the section highlighted with black shows the delay between the wake-up event and the arrival of the shockwave. So now we have a data acquisition system that offers ultra-low power consumption and can record the full shockwave pattern. But we also had to implement a reliable gunshot detector. Our algorithm has 3 stages and it has a hierarchical structure. The first 2 stages are responsible for filtering out false wake-up events. And the third stage implements the most complex part of the algorithm, the gunshot detection part, which relies on the detection of shockwaves. I don't want to go into much detail because you can read the full algorithm in the paper, but it tries to find shockwave candidates in the recorded signal, then extracts 10 features and assign a score between 0 and 1. That was the probability that it was actually a shockwave. The final outcome of the detector is a score between 0 and 1, which represents the probability of gunshot containment in the particular recording. Testing. We carried out many tests and many real-world tests. For example, during the second such a test, the device was worn by elephants for 2 weeks in the San Diego Zoo, and in the picture you can see the deployment of this prototype. And we also have a ongoing test in Kenya. We sent 2 prototypes, and one of them has been already deployed on a wild elephant. You can see the first prototype design on this slide, and on the left you can see the first prototype is being filled with resin before deployment. This first prototype contains additional components like an SD card and a constant running accelerometer. These are supporting the development of the final version of the system. We evaluated the power consumption of the first prototype. We estimated the rate of wake-up events from the data collected on elephants in San Diego. And in deep sleep mode, this first prototype consumes 250 microamps, which is a very low power consumption, but our final version will consume around 100 microamps. The estimated lifetime of the first prototype is around 8 years, which seems like an overkill, but we are now using huge batteries, so in the future, smaller batteries can be used, enabling the use of this system on a bigger variety of animals. We also evaluated the classification algorithm. We collected various noises like elephant noises, various impulsive nature noises, and mechanical impacts, and we also collected 71 totally independent gunshots to evaluate the classification algorithm. And on the upper left figure, you can see the histograms of the outcomes. The yellow, blue, and green rows are all negative samples, and they represent each subgroup of the collected data set, and the red samples are all positive samples, and a clear separation can be observed between the negative and the positive samples. So our classification algorithm distinguished noises and gunshots well. Just for a quick comparison between our solution and the state of the art, it has many advantages. For example, scalability, because this device protects an animal, not an area. It scales well. A quick summary: so we developed a wearable gunshot detector. It offers ultra-low power consumption, so the lifetime is acceptable. It uses a acoustic delay line structure and a two-domain base classification algorithm, and we carried out real-world tests and evaluated our algorithm on real-world data. So thank you for your attention, and I'm happy to answer your questions.